Good morning. This is Algebra 1, Lesson 7-6, and we have some students with us today. It's going to be sideways, so it's going to look a little weird. There's a few there, a few back this way, and I don't know if I can make it turn all the way. It's kind of blurry right now. Can I get the last few? There's Ashley. Okay. All right, so let's go back down here. And we are looking at this lesson. Okay. Now, you have analyzed exponential functions. Now you're going to solve problems involving exponential growth and solve problems involving exponential decay. We did talk about that a little bit yesterday. All right, the number of weblog, I can't say that. Is that a real word? Weblogs. I would think it would be web blogs, but I don't see 2B. Anyway, whatever. Or blogs increased at a monthly rate of about 13.7% over 21 months. The average number of blogs per month can be modeled by this equation. Y equals 1.1 times the quantity 1 plus 0.137 to the t power. Or simplified, you can add what's inside, but we will see the parts of that when we do exponential growth. Okay, or 1.1 times 1.137 to the t power, where y represents the total number of blogs in millions, and t represents the months since November of 2003. Okay, and then we have this graph. Note if we drew a line connecting all of the tops of the bars, they would create, a exponential curve, right? All right, so let's look at this. Exponential growth, things that grow. The equation for the number of blogs in the form, in the form of y equals a times the quantity x plus r to the t power is the general form for exponential growth. And we use this also a lot with investment, which we talked a little bit about yesterday. Let me see if I can focus that a little bit better. I don't know. It's not doing great. Anyway, so A is the initial amount that you start with. Web blogs or money in an account or whatever is growing. Population of bunny rabbits, whatever you're starting off. That's the initial amount. Times 1 plus the rate. Now, why do you think? Can anybody guess why it's 1 plus the rate? What's the 1 stand for? Where it crosses what? Okay, what'd you say? Okay, well, if we just multiplied what we had at the beginning times the rate to the exponent, the rate is just the amount of increase. We have to think about the amount when we multiply here that it was from the beginning, right? So if you had $1,000 in a savings account, you wouldn't just, when you go back a year later and want to know how much you've made that year on that savings account interest rate, if you made, I don't know, $35, let's just say, that's a silly amount, but I'm just pulling it out. If you made $35, you wouldn't want them to go, oh, you have in your account now just $35. You'd be going, where's my $1,000 I started with, right? So this is what this 1 is about. If they don't put that 1 in there, it won't account for the initial amount once they multiply it. It would just account for your amount of increase. Okay, so you have to have that 1 in there. All right, now t is the time. R is the rate of change expressed as a decimal. R is greater than 0, we are going to have a growth, right? Y is the final amount, what you would have in the end after that amount of time. We may be talking about money, we may be talking about rabbits, we may be talking about bacteria in a petri dish, cells, whatever. We're talking about things that are growing, okay? Exponential growth. All right, so let's go on to this. Can zoom in a little. I think that might help us. Well, Okay. Now, the prize for a radio station contest begins with a $100 gift card. One day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. And so if they don't call within 15 minutes, the next day, somebody gets another chance, right? They're going to call somebody else. But it would be more money. Write an equation to represent the amount of the gift card in dollars after T amount of days with no winners. Well, they're saying, what's the general form of this? So we take our basic exponential growth formula, y equals a times the quantity 1 minus r to the t power. That would be great to have in your foldable or in your cards, right? This equation. All right. Now, we put in what we do know. We started off with A being $100. We have the 1, because that's going to represent the initial amount once we multiply. And then the rate of change, or the growth, 2.5% change to a decimal is 0.025, right? Okay. Now, that's raised to the t power. This is an exponential growth, so the variable is up in the exponent. Now, so we're going to add those two things together. We get, now let me ask you this. If we want it, could we simplify this by multiplying 100 in here and raise it to the t power? What do you think? Justify your answer. Defend what you think.
Because it would change the outcome.
It would change the outcome. Because why?
Whatever t is, if you multiply 100 times 1.025, and then you would get a much higher number than what was originally going to be used.
Okay, that is correct. That's very true. You would get a much higher number than you would actually need or be truthful about. So the thing is, 1.025 is the only thing being raised to the t power, not the 100. So you have to be careful there. So you would raise it to the t power first and then multiply it by 100. Following, please excuse my dear Aunt Sally, right? Okay, in the equation y equals 100 times 1.1025 to the t power, y is the amount of the gift card, and t is the number of days since the contest began. Okay, how much will the gift card be worth if no one wins after 10 days? All right, so it's going to keep increasing in an amount. Now, don't forget, so this is just a little side note here for a second. If you had $100, the first day was $100, nobody calls in on time, so how much is it going to be the next day? Well, what is 0.25% of $100?
$2.50.
$2.50. So, how much is it going to be worth the next day?
$102.50.
$102.50. Okay, Grantlin, what do you think it's going to be worth the next day? Be careful there, because it's growing each day by 2.5%. So let's look at this. Do you think, okay, so the first day was $100, day number 1. Day number 2, it was 102.50. Day number 3, that's what we're looking at. These are dollars. Okay, so day number 3. The question here is, what is 2.5% of $102.50? Excuse me. Do we just add another $2.50? No, that's correct. Because now I'm getting $2.5%. Well, you can't even see that. I'm sorry, it's way out of bounds. I am getting, it's not going to be just adding another $2.50 to down here, because you're now making $2.50 on $102.50, not just 100. So take in your calculator, I'll do it up here. So we're going to take, I don't think, if you can see that. Turn it on. So we're going to take 0.5 times 0.025. So actually, instead of the second day, instead of making $2.50, you're making $2, or it's increasing by $2.56. Okay? And you may think, well, that's not that much. So we would have to add, for the next day, we're going to add 2.56. So that is 102.5 plus 2.56. So $105.06. Okay? Instead of $105. Now, you may think, well, that's not that much. But when you are talking about exponential growth, it changes a lot if this money were, say, $10,000 or maybe $50,000 or whatever. Or you wait. See how I told you when you talk about exponential growth, it grows slowly at first, but all of a sudden it just keeps, and then, as one day gets bigger, the next day is even bigger than that, and the next day is even bigger than that. So after you wait a while, that really growth out there a little bit is huge. Okay, now Einstein, I started talking about this yesterday and forgot where I was when my friend Fabian was reminding me of our friend Einstein. But Einstein said that interest, which is exponential growth, is the most powerful thing that has happened in modern times. And he was around when the telephone was invented. Because interest is either working for you or against you. Right? You're either paying interest or you're making interest. So try to be on the side of making interest way more than on the side of paying it. Okay? All right. So here we go. Now, so it says, how much will the gift card be worth if no one wins after 10 days? We put 10 in there for the number of days. And now don't forget, we're multiplying this, or taking this to the 10th power first, and then multiplying it times 100. So let's see what this would look like. So if we took 100 times the quantity, 1.025, and then parentheses. Now you can do your caret there, and this is to the 10th power. So this should, if you have a calculator like mine, this should raise only the 1.025 to the 10th power. If I had put the parenthesis around the whole thing, then it would raise everything to the 10th power. So, in 10 days, the winner could get approximately $128. Let's see if we're right. And 1 cent. They rounded it to the nearest penny, which is wise because we are dealing, where's my finger? Oh, there it is. With pennies right there. Okay, good. So now, let's get out and I'll hide this for just a jiffy. Get out your handy-dandy boards. Yeah?
I have a question. So when I did it the way they do it in the book for the third day, I come up with $107.68.
For the third day? Or are you talking about the third? The first day was $100. So that's probably their third change, because we only did 2, right? We increased, so you see what I'm saying? They're probably saying the third day was actually our 4th day. Do you see what I'm saying? That's the third increase.
That's what
Okay.
by the third exponent.
Yeah. Then that's what they're talking about. I consider day 1 as having $100 because, well, that's what they said. But, yeah. Okay. So a college tuition has risen 5% each year since the year 2000. If the tuition in 2000 was $10,850, write an equation for the amount of tuition T years after 2000. Then we're going to predict the cost of the tuition for college in 2015, which is already past us, but this book was written before 2015. Okay, so you go ahead and try to work this out. Where's your board there, my brother? Get your boards out. Okay. So, our interest rate is 5% since the year 2000. So, T is going to be the number of years since 2000. If the tuition was $10,850, so 10,850 is going to be your what? A. That's correct. So, here's our equation. Y equals A times the quantity 1 plus R to the T power. And so we're going to have Y, that's going to be the current tuition when we're finished. A, 10,000, what did I say? 850 times the quantity 1 plus the rate, 0.05 to the T power. Now we can simplify that by adding those two together. So we could get Y equals 10,850 times 1.05 to the T power. Now, that looks right. Yes, good. They rounded it to the nearest penny though, but yes. Okay, so if we do this on the calculator, it looks like everybody's doing a good job. So check your work with what I'm doing here. So we're going to have 10,850 times 1.05 to the T power. To the T power. So this is your first answer. So now it asks, how much will it be in 2015? Well, how many years are there from 2000 to 15? 15, right. And then enter. So $22,556.37. That's a lot. So here we go. Let's do a good job and get really high scores on the SAT so you can get some scholarships going on, right? Okay, good. And they wrote about because we had to round it. Anytime you round, you have to write about. Okay, so here we are at the next compound interest, and this is talking about money. It looks very, very similar to what we were just doing, but we have a little extra something going on, N. Okay, compound interest is earned or paid on both the initial investment and the previous earned interest. That's why I was saying you don't just earn the same amount every $2.50, $2.50. It grows a little bit more every day because you're earning interest upon interest. So that's why Einstein was either saying it's working for you or against you. You are either paying interest upon interest or you're earning interest upon interest. That is why I think I talked about it, why President Obama's administration added that thing to when you get a credit card in the mail. And it tells you if you just pay the minimum amount, it will you won't get it paid off until however many years. But if you pay this little bit more, and it's usually not very much more, you'll get it paid off in how many years? And it's usually way, way, way less. So I would really suggest you always pay a little bit extra on the principal no matter what you're paying on. Your house, your car, your student loan. If you don't have that, yay for you. Or a credit card, hopefully you don't go down that road, but if you do have one and you're paying interest, pay a little bit extra every time. Just go in, they'll have websites, I'm going to pay $20 extra, okay, on the principal, put it on the principal, and that will take it off of this big P if this is working against you, okay? All right, so here we go. A is the current amount, so that's whatever you're going to have at the end of a certain time. It's very similar to the original. P is the principal or initial amount. That's what you had at the beginning, just like it was in the other one. Then we have the 1. Now our rate is divided by N. And this is the rate here because compound interest is growing for you, hopefully if it's in a bank or in an account or a Roth IRA or whatever it's in. N is the number of times the interest is compounded each year. So if it's compounded yearly, it would be once. N would be 1. If it's compounded biannually, it would be compounded twice. If it's compounded quarterly, how many quarters are in a year? 4. Okay? So you have to, or if it's compounded monthly, how many times is it compounded?
12.
12. Okay. Now, we're not doing that this time, but their interest rate on a credit card that you're paying, they compound that what's called continuously.